Okay, let me just go to full screen. Alright. Welcome everyone to week 3 of our NPTEL PMRF problem solving sessions for the course Electronic Theory of Solids. Let me see. Okay. Yeah. So first of all, a brief introduction of mine. I am Akshay. I am a PG student, PMRF, in the Solid State and Structure Chemistry Unit, SSCU, of the Indian Institute of Science, IC, Bangalore, India. I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering, and I am an NPTEL PMRF TA for this course, Electronic Theory of Solids. Alright. So because of some technical problem with my tablet, today's session is starting at a rate actually at 6 p.m. Sorry for the inconvenience. Right. The recording will be provided on the YouTube. Alright, so let us quickly start with today's session. Okay, just 1 minute. Let me check if the recording is. Right, I guess. Okay, recording is okay. Right, let me go to the screen. Alright. So let's start with today's session. Okay, so first we will start with our problem number 1. So problem number 1, what we have is the energy eigenvalues of a particle of mass m confined to a rigid one-dimensional box of width L are En equals to n will be 1, 2, 3 our integers. Now if the walls of the box are moved very slowly toward here, so the walls are moving towards each other very slowly, and let's say okay, so by some rates at dl by dt, what is the rate of change of the energy dE2 by dt of the first excited state? Alright, so basically this is a problem of particle in a box that we know in a simple problem of particle in a box in quantum mechanics, and what it is saying is that in this case what we are having our particle in a box, it is the walls are coming closer to each other by very slowly, and then if we change this thing, if we are changing, basically we are changing the L value, the length of our the width of our box is changing, then it is asking what is the rate of change in the first excited state. Alright, so that's the problem. So this is basically for a 1D particle box. Now we know that for 1D particle in a box, okay, which is let me just draw the schematic as well. So this is our 1D particle in a box. So the particle remains enclosed between this from 0 to L. The particle can only move from 0 to L only. Alright, so we know that for particle in a box we have h cap psi. So this is our Schrodinger equation, which is Hamiltonian, and the energy eigenvalue we can take it as E. Alright, so I can write my Hamiltonian as minus h phi square by 2m del square psi by del x square, and there is no potential, equals to E times psi. Alright, then from there, so I'm just quickly going to derive this thing once. So I'm not sure if it is derived in the lectures or not for particle in a box. Okay, sorry. So this I can write it as minus 2me by h phi square psi, and this we can take as our k square. So our k is equals to under root of 2me by h phi square. Right, so I can write this del square psi by del x square is equals to minus k square psi. Alright, so from here we have this, and from here I can take my psi x, and I will call it psi k of x is equals to a sine of kx. Okay, so this we can see that because of the boundary condition. Also we have a boundary condition. Let me just write the boundary conditions. So we have this equations. Okay, we have this equation, and we know we have the boundary conditions, and the boundary conditions are so boundary conditions we have is psi at x equals to 0 is equals to psi at x equals to L equals to 0. Okay, so looking at this equation, this final Schrodinger equation that we have, and the boundary conditions that we have, we can take our psi of x, and I will call it a psi with a subscript k. So our wave function will be also depending on k. I can write it as a sine of kx. Okay, so you can check that this solution of a wave function that we have taken, like a sine kx, it is going to satisfy this equation and also our boundary condition for particle in a box. Okay, so this is our wave function, and first of all this is going okay. So and if we can say that it satisfies the boundary condition, and to satisfy the k equals to L boundary condition, now we have at psi equals to L, it has to be equals to 0. It means sine KL has to be equals to 0. So KL should be equals to some n pi, where n will be our integer 1, 2, 3 and so on. So k comes as n pi by L. From here we get our so basically we have derived our k from here. K will come as n pi by L. Alright, and then so our psi k of x, now I can write it as psi n of x as a times sine n pi x by L. Okay, so this is our wave function now of our particle in a box. And E of n, okay, the energy eigenvalue. Now we know that if this relation k is equals to under 2me by hy square, so our energy E will depend on k as hy square k square by 2m. And now we have our k is given by n pi by L, so our energy, which will now depend on n, will be equals to n square pi square hy square by 2m L square. Okay, we just have to put k is equals to n pi by L, this k equals to n pi by L, in this ek, which is hy square k square by 2m. So this is the solution. I have not normalized the wave function. You can normalize it as well. There will be another question particle in a box, so I will normalize it there. But basically for this problem, what we need is just this eigenvalue. Alright, so we just need this eigenvalue of particle in a box. Okay, this is the energy eigenvalue. Values for particle, for 1D particle in a box. Okay, simple particle in a box problem. Now the problem is that has been asked it. We have to find dE2 by dt. So it is said that we have to find the change in the first excited state when we are moving our balls towards each other. So from here, now for first excited state, so here in the question it is already mentioned that for first excited state it is E2, that is n equals to 2. But this is important to remember, like if we are saying that first excited state, it means n is equals to 2. When we say ground state, for ground state means n is equals to 1, that is the lowest energy. When it said first excited state, then n equals to 2. If it said if it says second excited state, it means we have to take n equals to 3. Okay, so like we have this kind of energy, n equals to 1, n equals to 2, n equals to 3. So this is our ground state. This is our first excited state, and similarly this will be our second excited state. So this is just for precaution, like sometimes in problems people get confused, like it is given second excited state and they take n equals to 2. So for second excited state, remember that n will be equals to 3. But for this problem it is already given as well in the problem, and let me just mark it as some different color. Okay, so this is just for your information. This is not important for this. Okay, I can't change it. Okay, let it be like this. Okay, let me just this thing. Okay. So this is not for this problem, but this is important that you should remember that you should not get confused. Like if it is second excited state, and n should be equals to 3, and should be whatever the excited state plus 1. Now here it is in the question it is said it is for the first excited state, so we have to take n equals to 2. In the problem also it was written. So for our first excited state, our E2 we know will be given by we just put n equals to 2 here. So we get 4 pi square hy square by 2 m L square. Okay, 2 square will be 4, and so from here we can find E2. So our E2 is 2 pi square hy square by m L square. Alright, and what has been asked is dE2 by dt. That is what is asked to us. Okay, so all these things, 2 pi square h pi square by m, they are going to be constant, and we just have to take d by dt of 1 by L square. Okay, and we have 2 pi square h pi square by m. I can write this as minus 2 times L cube times dl by dt, and dl by dt is given to us. It is said that the walls are coming very slowly towards each other, so so we can take that rate is dl by dt. Okay, how the L is changing. And then okay, and in this one just take but we will have a minus sign here. Okay, and there so L we can take is a negative value. L will also be negative, so overall this dE2 by dt will be a positive value. Alright, so basically what we have is minus 4, but let me just write it in. Okay, I can write, okay, let's just write it. Okay, so I will write it as minus 2 by L square. Okay, minus 2 by L. Okay, let me just write it as minus 2 by L. I will take minus 2 by L, and I will write 2 pi square h pi square by, okay, so that will be ml square. Okay, so why I am writing this? Okay, here we can see that we have 2 pi square h pi square by ml square. This is my ml square, and this will be our E2, as we have seen here. E2 is 2 pi square h pi square by ml square. So this will be E2. So basically our dE2 by dt will be equals to minus 2 E2 by L dl by dt. Alright, so that will be answer. And here we can see that here now dl by dt is some minus alpha, where alpha is greater than 0. Okay, because what we are seeing is that they are coming closer to each other. Okay, they are moving slowly towards each other. So these walls, they are moving towards each other, so our L is decreasing. Okay, so dl by dt is less than 0. Okay, so since dl by dt is less than 0 and it is for alpha greater than 0, I can write it as d. Okay, I should have written it there. So let's take so I am taking this dl by dt. Let dl by dt is equal to some negative alpha with alpha greater than 0. So dl by dt is less than 0. We are decreasing our L. So dE2 by dt will be equals to, if I take minus alpha, it will be 2E2 by L times alpha. Alright. So here we can see that dE2 by dt is greater than 0. Alright. So what we have basically derived here is that when we are decreasing the value of L, then our so this is how our first excited state energy will change with the rate of the change of this L. And also, since we are decreasing the L, our energy values will start to increase. Our excited state energy will be increased, and that we would have expected, because our En formula is inversely proportional to L. So if we decrease the L value, then all the energy drivers will increase. And in this problem, it is asked for just to find the rate of change for the first excited state. So we have calculated it. Alright. Okay, so this was our problem number 1. So let's go to problem number 2. Okay. So in problem number 2, what has been asked is a particle of mass m is confined to an asymmetrical box of unit length in one dimension. Okay, so now we have this is again a particle in a box problem, and we have an asymmetrical box this time of unit length of in one dimension, and it is described by the wave function psi x equals to some wave function is given to us for x between 0 and 1, and it is 0 outside this interval. Now what is the expectation value of energy in this state? Alright, so okay, I forgot to do the normalization there, so let me just do. Okay, again for particle in a box, okay, 1D case. Okay, for particle in a box 1D case, we have seen that it is energy is equal to n square pi square Okay, so it is given by En is equals to n square pi square h5 square by 2ml square. Alright, this is the energy value. We also find psi n of x, but I forgot to normalize it. Okay, I knew there was one question, but I forgot. Okay, let's just normalize it here. Okay, so this is given by n pi x by L. Okay, this is also we have seen in the last problem, and after normalization, so normalization basically means integrated from 0 to L, psi n star of x, psi n of x dx. This has we have to equate it to 1. Alright, so if we normalize it, you will have mod of psi n whole square dx is equals to 1. So integrated from 0 to L, a square sine square n pi x by L dx equals to 1. Take out a square here, and I will multiply and divide it by 2, and 2 sine square theta is 1 minus cos 2 theta. So 1 minus cos 2 n pi x by L. I will integrate it from 0 to L. So I am doing it for a general particle in a box 1D case. I am just doing the normalization. Okay, and if you do this integral, cos will become sine, and sine of 0 will be 0, sine of L will be 2. If I put x equals to L, then that will be sine of 2 n pi. Alright, so this cos and integration will give me this will give me 0. Alright, so you can do and check this integral, and 1 will be integrated to L. So our normalized this constant will come as under root 2 by L. Alright, so this you must already know. So sin n of x, what we have is under root 2 by L sine n pi x by L. Right, and let me just take this as well. Okay, let me just put let me just put it here. Okay, so we have these two things for our particle in a box case. Okay, so for a particle in a box we have this thing, and what we are having is that basically in this case what we have we have this particle in a box. We know the general solution for this particle in a box, and what it is saying is that a particle mass is confined in an asymmetrical box. Okay, so somehow this is not symmetrical. The box is a little bit shifted. You can say it is not symmetrical. So instead of being symmetrical, you can say that the box is a little bit shifted or something, like there is some form of shift that I'm not exactly sure, but let's say this is not kind of symmetrical. Okay, so but the case but it is same as a particle in a box case only, but it is just that it is not going to be symmetrical. But we know the solution for a symmetrical particle in a box, and that we have divided here. L is equals to 1. Okay, so I can write sin n x is equals to under root 2 times sine n pi x. Okay, let me just write this, because it is said that this is a unit box, unit length box. So we will if it was symmetrical, then the wave functions and the energy eigenvalue, they are going to be this n square pi square h5 square by 2m. Okay, for L equals to 1. So this will be our wave function. If this would have been our wave function if we have this box was symmetrical. If it was symmetrical, then it would have been the same case as we have for a simple particle in a box. But now it is not symmetrical, while the wave function is given like this. So whatever the wave function, so our electron is within an asymmetrical box. It is not the same. It is not just symmetrically 0, but there is some change is there, because of which our wave function is like this. And it asymmetrical box means that it's not like your potential is continuously 0. So basically somehow you can say that let's say, oh, okay, yeah, okay, yeah, so like this, okay, like initially, like we are saying that okay, there is no potential, but there might be, like, okay, it could be something like this, some asymmetrical stuff is happening. So like there is some zero potential, and there might be uh, it would not be like not exactly symmetrical. So here you can see that this for this box, particle in a box case, it is symmetrical, it is same on both the side. But this might be asymmetrical, like in this case there might be some zero and there might be some energy is there is already some extra energy is there. So this kind of, okay, so okay, yeah. So this kind of asymmetrical picture, and I'm not drawing the picture because I am also not sure what is the exact picture would be, uh, that you can try it out, but this is the kind of asymmetrical. So it is not, this is symmetrical, this is symmetrical, and the asymmetrical, okay, let me just draw maybe something like this, okay. So like you have similar particle in a box problem, but it is not like here it is something different box, and here let's say it has some increased energy or something. So it is not it is not symmetrical in that sense. All right. So because of that we have some wave function now, and what has been asked us is to find the expectation value of the energy in this state. All right. So for this case what we can do is we can write our psi x function. So we have, so because of this some form of asymmetry, our wave function is basically, we can see that it is given by sine pi x times 1 plus cos of pi x. Alright. Now what we can do is, if we multiply it here, under root 8 by 5 sine of pi x plus under root 8 by 5, I can take it as sine pi x and cos of pi x. Alright. Now this so this thing we can see that if so we will try, what we will do is, we know this solution wave function for the particle in a box case, simple particle in a box case, symmetrical case. So for we will try to write this wave function within this basis, within the base, within this psi n of x. So what we can do is, if I take under root 8 by 5 and if I multiply and divide by root 2 sine pi x, okay, and here let me do under root 8 by 5 and let me multiply it by 2 root 2 here, and let me multiply it by 2 root 2, so there will be a root 2, and then if I multiply 2 sine pi x cos, okay, let me write right now 2 sine pi x cos of pi x. Alright. So now here this thing 2 sine, this is like 2 sine theta cos theta, so you will get sine 2 pi x. Alright. And then we can see that this thing, you can see that it is root 2 times sine n equals to 1, so it is our psi 1 of x, and this one, that will be when this will become sine 2 pi x, so it will be root 2 times sine 2 pi x, so it will be psi 2 of x. Alright. So basically we can write our psi of x as, okay, and there is like 1 by root 2 here, so I will have I can write it as under root 4 by 5 psi 1 of x, okay, plus this 2 by root 2 will get cancelled out, so I will just write it as under root of 1 by 5 psi 2 of x. Alright. So our wave function psi of x now could be written in the basis of these two, our ground state and the first excited state, wave function of the ground state and the first excited state. Okay, so because of some asymmetry, now wave function has changed. Okay, so the wave function has changed. Okay, but and then using this function, what is the expectation value of energy in this state? Okay, so it is still, but the problem we can take this, that this so it is not exactly some energy, maybe because let's say there is some kind of asymmetry. Basically this these two areas are not same, there is some form of asymmetry, symmetrical is there, so which is not mentioned, but we can consider that still there is no basically for the whole, if we take the Hamiltonian, we will consider that the Hamiltonian remains more or less the same. The Hamiltonian is for the particle in a box, but since the particle in a box problem is not, this thing is not symmetrical, somehow we have our electron in this kind of a state. Okay, and it is now asking us the expectation value of energy in this state. So expectation value of energy we know is given, will be given by this psi of x, h cap psi of x. All right, now here it is not mentioned like how it is like exactly changed, so we can assume that we will assume our Hamiltonian to be the same as we have for a particle in a box. Okay, and so we will just consider that for a unit particle in a box, whatever our Hamiltonian is, our Hamiltonian is just the same, and just because of, you can say, some perturbation within this thing, because of this because the surface, because it is not symmetric, the potential is not symmetric, not symmetrically zero, because of some sort of perturbation, you can say small perturbation or something, the wave function has become, we can see that it has become a you can say a combination or a superposition of our ground state and the first excited state. So our electron is now in a superposition of our ground state and our first excited state, as we can see here. So because of some form of perturbation, you can say, within the potential, this has happened. But overall, we can say that our Hamiltonian, we can just consider that our Hamiltonian is same. So I'm just going to consider that this is the same Hamiltonian. So our h cap is, I'm just going to take it as minus h square by 2m del square by del x square. Alright, I will just take it as the for this one I will just take it just our particle in a box case. Now psi of x, I can write it as root 4 by 5 psi 1 of x plus under root 1 by 5 psi 2 of x. So I'm using the Dirac notations. So if you are not familiar with Dirac notations, I would recommend to go to Introduction to Quantum Mechanics by David J. Griffiths. In today's session also we will solve some small problems on the Dirac notation, so you will get more familiar with it. But I would recommend to go through that, because that makes things very simpler. So hello, yeah. So the book is Introduction to Quantum Mechanics. Let me just write it. Reference. Introduction to Quantum Mechanics by David J. Griffiths. So this is for introductory quantum mechanics. This is a very nice book. So if you want a good introduction on this, on basics of quantum mechanics, or Dirac notations and all, and also for the, I guess there is in the appendix there are section on the eigenvalue problems as well, linear algebra as well. So you can so I guess this is a very nice book, right? If you have any doubt in basics of quantum mechanics, this is a nice book, Introduction to Quantum Mechanics by David J. Griffiths. We will solve some simple problem from this book as well in today's session, right? So now we have to solve this problem. So from here we will get 4 by 5 times psi 1 h cap psi 1 plus, you can take, this will be 4 by okay, so this will be under root of 4 by 5, which will be 2 by 5 psi 1 h cap sorry, this is psi 2 plus this will be 2 by 5 again psi 2 h cap psi 1. Alright, and then this could be written as 1 by 5 times psi 2 h cap psi 2. Alright, so basically what I have written it directly, but maybe I should not skip that step. I should write it in a proper manner, not skip this step. Okay, so basically what I have written here, I can write this as root 4 by 5 times bra of psi 1 plus root 1 by 5 bra of psi 2. Right, this you will have your operator h cap, and you will have root 4 by 5 psi 1 plus root 1 by 5 psi 2. Alright, so I've written psi x is this, and then I have breaking down it into this bras and caps. Alright, this is the Dirac's bracket notation, and then you just have to take each one of them. So you take like this one h cap, with this one you will get this 4 by 5 psi 1 h cap psi 1. Okay, and similarly you have to pick out each of the terms. From here we will get this 4 terms, and here from here sorry, you can check it. Okay. Okay, now from here we know that that for this particle in the box, psi I psi j will be is equals to del of ij. So this science, they are normalized, which means it is equals to 0 for I not equals to j, and it is equals to 1 for I equals to j. Okay, and also if I apply E cap on some psi n cap, then what I get is En times psi of n. Alright, now using these two equations, alright, let me just make it this. Okay, using these two ones, if you see here, this psi 1 h cap psi 2, this will be equals to 0, and also this psi 2 h cap psi 1 will be 0, because h cap will act on psi 2. This will give you E2 times psi 2 times psi 1, times psi 1, alright, which you can then write as, you can take out the E2 because it will be a scalar. You will have psi 1 psi 2, okay, and this will be 0. Okay, this will be 0 because psi I psi j is a canonical delta ij, and I is not equal to j, 1 is not equals to 2, so that's why this bra psi 1 cat psi 2 will be equals to 0. Alright, so just using this relation, so what we are getting our expectation value of energy. We can get 4 by 5 times the remaining terms, which is psi 1 h cap psi 1 plus 1 by 5 of psi 2 h cap psi 2. Alright, and this we know, this is basically our E1, and this is basically our E2 energy. Alright, this will be E1 E2, and okay, and I will write my En as n square pi square h pi square by 2m, and it is unit length, so I am just using 2m here, and I can write this as n square times E naught. So here E naught is equals to pi square h pi square by 2m. Okay, so I am just taking, this is the you can say the ground state energy. So our average energy E will be equals to 4 by 5 times of, now E1, so what is E1 is going to be, it will be 4 by 5, same pi square h pi square by 2m plus 1 by 5, it will be 4 times pi square h pi square by 2m. So I can write my average energy as 4 by 5 times of E naught plus this will be also 4 by 5 times of E naught, so it will be basically 8 by 5 of E naught. So our average energy now will be equals to 8 by 5 times of E naught. Okay, and E naught is basically our ground state energy. Alright, so this was the problem. This was our problem number 2. Okay, so let's move to problem number 3. Alright, so in problem number 3, it is given that we have a triangular Bravais lattice is spanned by the basis vectors E1 vector and E2 vector, which are given root 3 and Ex. Let's say these are Ex cap and Ex and Ey cap. Yeah, so these are vectors only. It is that where Ex cap and Ey cap are the unit vectors along the x and y direction respectively. Find the reciprocal lattice vectors. Alright, so let b1 and b2 vector are the reciprocal lattice vectors. Alright, now we know that. Now for the in today's session we will also uh, we will also see a formula for this reciprocal lattice vectors that you might already know. But for this problem, what we will do is we will just solve this problem using this relation, that ai vector dot bj vector is equals to 2 pi times del of ij, which gives us 2 pi for I equals to j and 0 for I not equals to j. Alright, so this relation, this is basically this you should always remember, like for the primitive lattice vectors and the reciprocal lattice vector, this is the relation ai vector dot bj vector is 2 pi times del of ij. And so I will not use the formula, but I will just assume that I just know this relation, and from here we can say that it is b1 times ex cap plus b1y ey cap, and our b2 vector is b2x times ex cap plus b2y ey cap. Okay, so basically we want to find this reciprocal lattice vector, and we have basically now we have 4 variables. Okay, ex cap is basically just x cap y cap. Okay, and from here we also know that ex cap dot ex cap will be 1, ey cap dot ey cap will be equals to 1, and ex cap dot ey cap will be equals to ey cap dot ex cap equals to 0. Alright, because they are unit vectors. These are like unit vectors along x and y directions. Alright, and now from this relation ai vector dot bj vector is 2 pi times del of ij. What we have is a1 vector dot b1 vector will be equals to 0. Similarly, it will be equals to 2 pi, and e2 vector dot b1 vector will be equals to 0. Okay, and also we know that similarly we will have a1 vector dot b2 vector will be equals to 0, and this e2 vector dot b2 vector will be equals to 2 pi. Alright, so this is also the relation that we have. Now so basically we have this 4 equations. I can say these are 1, 2, 3 and 4. We have this 4 equation, and we have 4 variables, so we can just solve this 4 equation and find this 4 variables. From there we can say that a1 vector dot, so I will use a1 vector dot b1 vector. Okay, a1 vector is given to us, so a1 vector is root 3a times e of x cap. So first I will use a1 vector dot b1 vector equals to 2 pi. Okay, so let me just start with this using equation 1. a1 vector dot b1 vector is equals to 2 pi. Okay, and a1 vector is given as root 3a ex cap dot b1x ex cap plus b2 b1y ey cap equals to 2 pi. So from here now ex cap dot ey cap will be 0. So what we will get is from here is root 3a b1x is equals to 2 pi. So b1x will be equals to 2 pi by root 3a. So from this equation 1 we have find b1 of x. Similarly, using equation number 2, okay, let me just write equation number 2 for this, and let's say this is equation number 3. Okay, so equation number 2 is e2 vector dot b1 vector is equals to 0. So I take the dot product of this b1 vector with e2 vector. Now e2 vector is given to us as root 3a by 2 ex cap plus what we have is ex cap plus root 3 ey cap. Okay, root 3 by 2 is common, plus root 3 ey cap. You have to take dot product with b1 vector, which will be b1x ex cap plus b1y ey cap, and that has to be equals to 0. So I can take this root 3 by 2, I will just move it to that 0 side, so that is not needed, and ex cap dot ey cap will be zeros, and ex cap dot ex cap will be 1, ey cap dot ey cap will be 1. So from here we will have b1x, right, from ex dot ex, and I will have root 3 times b1y equals to 0. So my b1y is equals to minus b1x by root 3, and b1x we have already found is this. So my b1y will be equals to minus 1 by root 3 times b1x is 2 pi by root 3a. So from here b1y will be equals to 2 pi by 3a, minus of 2 pi by 3. Alright, let me just check if I am doing right. Okay, minus 2 pi by 3a. Okay, similarly we can find for using equation number 3. Alright, so equation a1 vector dot b2 vector equals to 0. Okay, same thing we have to do, and our a1 vector is root 3a times ex cap take the dot product with b2x ex cap plus b2y ey cap equals to 0. What we get is root 3a times b2x, that has to be equals to 0. Alright, because ey cap will be automatically 0, so our b2x will be equals to 0. Okay, so our b2 vector will have no component in x direction, and then using equation number 4, okay, again equation number 4 is basically the relation that we have, which is e2 vector dot b2 vector equals to 2 pi. So e2 vector dot b2 vector equals to 2 pi. Now here I already know that b2x is 0, and a2 vector is root 3a, root 3a by 2 times ex cap plus root 3 times ey cap dot product. Now b2 vector, b2x is already 0, so I will just write b2y ey cap here, right, because b2x is already 0, the x component is already 0. Okay, and doing this, what we have, root 3 by 2 I can take there, that is equals to 2 pi. Okay, sorry, that is equals to 2 pi here. So what we have is 3a by 2 b2y equals to 2 pi. So our b2y is equals to 4 pi by 3a, right. So from here, okay, so we have found all these three okay, so we had 4 variables, and we have found the 4 variables. So basically we have found that our b1 vector is equals to b1x ex cap, which is 2 pi by root 3a ex cap. It will be 2 pi by root 3a ex cap plus b1y ey cap, which is minus 2 pi by 3a minus 2 pi by 3a ey cap. Alright, and I can take 2 pi by root 3a common here, so it will be 2 pi by root 3a ex cap minus 1 by root 3 ey cap. Alright, so this will be my b1 vector, one of the reciprocal lattice vector, and similarly, and the b2 vector, we just have the y component b2, because b2 of b2x equals to 0, b2y is 4 pi by 3a, so b2 vector will be equals to 4 pi by 3a ey cap. Okay, so this is our answer. Alright, and in today's session there is also you might know there is a formula also for to find this reciprocal lattice vectors. but and we will see this we will see that formula in one of the other question in today's session. But in this problem, even though if you don't remember the formula for how to write this reciprocal lattice vector, just remember this relation, that this is the general relation, that ai vector dot bj vector should be equal to 2 pi times del of ij. So if you are given some primitive lattice vector, you can just even if you don't know the formula for this reciprocal lattice vector in terms of primitive lattice vectors, then you can just use this relation, the main relation 2 pi that ai vector dot bj vector equals to 2 pi times del of ij, and then just assume whatever your reciprocal lattice vector is, let's say b1x, b1y, and if it is in 3 dimension, there will be a third component as well. And then just find, you will have this for the 3D case, you will have 3 variables and you will have 6 variables and 6 equations, and and the equations you will get from this relation, and you can solve them and you can find your reciprocal lattice vector, right? Or you can use the formula as well, and we will see that formula as well in one of the other problems. Alright, so that was problem number 3. So let's move to problem number 4. So in problem number 4, it is given that Bloch's theorem is about the wave function of an electron in a periodic potential. It is stated as psi of x plus a is equals to psi x times e to the power iota k. So this is our Bloch theorem, that if our wave function is moved by a unit of lattice vector, let's say we have in 1D, so psi x plus a, so our wave function will be the wave function psi x times there will be just a phase difference which is given, and the phase will be given by e to the power iota ka. Now we have to prove that psi x is equals to ux e to the power iota kx is also an equivalent form of the Bloch's theorem, where ux is the periodic crystal potential, where so it is u of x plus a is equals to ux. Alright, so we have to prove that this definition, that is also same as the definition we have for the Bloch theorem. So we will start with this definition now. So let given as, so we will assume that it is given to us that, so basically we will start with this, we will start with this, and then from here we will see that this thing is equivalent to our Bloch theorem, what we get from the Bloch theorem. So let's start that this is psi of x is equals to ux e to the power iota kx. Alright, now make a unit transition. Now make a unit transition to get, now we will just make a unit transition, so we get psi of x plus a. Alright, so psi of x plus a will be written as u of, let me write it as u of x plus a e to the power iota k x plus a. Alright, now using the periodic property of given potential, that is, so it is given that it is periodic, that u of x plus a should be equal to us. This is the periodic property that is given to us. We can write psi of x plus a as e to the power iota ka. I will take this there, e to the power iota kx times u of x. U of x plus a will be this, and I have just write e to the power iota k x plus a as e to the power iota k different, and e to the power iota kx. Now here we have taken this psi x as ux times e to the power iota kx. So this thing is basically our psi of x. Alright, so from here what we are getting is, basically if we are taking psi of x as ux times e to the power iota kx, and then we just made a unit transition, then what we are getting is that, as in that case psi of x plus a comes as e to the power iota k psi of x, and this is what we get from our Bloch's theorem as well. Alright, so this is what we get from our, and which is given from, which is the given form of Bloch's theorem. Alright, so this is what we get. This is what we get from Bloch's theorem. We can say this is what we get from Bloch's theorem. This is what we get from Bloch's theorem. Okay, if we consider our wave function as the periodic potential times the wave function, so that is what we get, and that's the same thing. Okay, so that also you have seen in the lecture as well. So this is just a proof that this form of wave function that satisfies our Bloch's theorem basically. If we take a wave function of this form, it satisfies the Bloch's theorem. All right, so let's go to problem number 5. All right. So problem number 5 is okay. Consider a linear lattice of we have to consider a linear lattice of length L with a lattice constant A. Considering the first Brillouin zone, the number of possible k values in any energy band is equals to. Okay, so we have to find the number of possible k values in any energy band. So what is given to us? We are given let's say we are basically given a linear lattice. Okay, so we have a 1D lattice basically, and the length of this lattice is L. Okay, so we have a lattice which has a total, we have a finite lattice basically, not an infinite one, so which has a length L, and the distance between each of these lattice point, that is given as A. Okay, so you can say that, okay, you can take like this as your unit cell of length A. Okay, so your primitive unit cell will be you can take something like this, okay, which has one of the atoms, okay, and then you can just repeat it and you can make your lattice, and it is given that the length of this, it is not a infinite lattice, it has a length L here. All right, now here using the periodic boundary condition, okay, so as a linear lattice of length. Okay, so lattice is generally again since this is a lattice, we can still consider, okay, so this is a lattice of length L, but but it is given a lattice, so we can consider that there will be a periodic boundary condition at the ends. Okay, so it is given that it is a linear lattice, and so basically we will be repeating there will be a period, because this is a complete lattice, we can consider that there will be periodic boundary at this 0 and at both of these end positions. Okay, so by periodic boundary condition we will consider that both these end positions will have will be similar, will have the same wave function. All right, so a wave function will be seen at this x equals to, let's say, 0, and this x equals to L. Our wave function is going to be same. So using the periodic boundary condition, we may write, okay, because this is just a lattice of length L, and then thus we can just repeat this whole lattice infinitely if we want an infinite solid. So we will consider that they will be similar at x equals 0 and x equals to L. So using the periodic boundary condition, we may write psi at x plus L is equals to psi x. Alright, so basically they will be same at this length, and if I repeat this complete unit cell, if I repeat here, so basically I can repeat this. So basically this is my unit cell with so this is my when we say lattice constant. So lattice constant is the smallest length of the repetition. That is our this. And when we say so it is said that it is a lattice. So basically we have a lattice of L, and then we can repeat that L lattice in both the direction, in the linear direction. So there will be this periodicity of the lattice as well. There will be periodicity of the lattice, okay, with respect to this L, and that's why we can write our wave function psi x plus L equals to psi of x. Okay, so this is the periodicity that we can write, and also using the Bloch's theorem. We can write our so just now we have seen that we can write our psi of x. So So I will write my psi of x as, let's say, u of x times e to the power iota kx. Okay, that satisfies my block theorem that we have just seen in the previous problem. So I can write as psi of x plus a. Okay, sorry. I will use the same. Okay, so I have this relation, periodic boundary condition. So I will use this relation, psi of x plus I is equals to psi of x. Alright, so that will, so and from the Bloch's theorem we have our psi of x like this. So what I can write it as u of x plus L, okay, e to the power iota k x plus L, that will be equals to u of x e to the power iota k x. Alright, because we can write our wave function in this form using the Bloch's theorem, and we have this from our periodic boundary condition. Alright, so using this, and also we can use it using this periodic potential ux plus L will be equals to u of x. Alright, so therefore, okay, u of x plus L will be equals to ux. So what we will have is, and e to the power iota kx will cancel out, so we have e to the power iota kl equals to 1 here. Alright, therefore this kl will be equals to 2 n pi. Okay, then e to the power iota kl will be equals to 1. Okay, I hope. Okay, so this is this is, you must know. Okay, you can just use this if you have any doubt, that e to the power iota theta is equals to cos theta plus iota sin theta. So you can just put theta is equals to 2 n pi, and then e to the power iota theta will be equals to 1. So that's why your theta has to be equals to 2 n pi, or we can say kl is equals to 2 n pi, with n equals to, you can say, plus minus 1, plus minus 2, and so on. Okay, it could be any of these integers. Now considering the first Brillouin zone, so our k, so from here, so let me just write, from here our k will be equals to 2 n pi by L. Right, now considering the first Brillouin zone, now remember that Brillouin zone, that will be defined by your lattice constant. Okay, so we have a lattice of length L which we are repeating, and that's why we have applied our periodic boundary condition on that, psi of x plus L equals to psi x, that we can apply. Alright, and then we use our psi x from our Bloch's theorem, and using that we get this relation that k will be equals to 2 n pi by L. Alright, but when we talk about our first Brillouin zone, then the first Brillouin zone, for this our k value will be from minus pi by a to pi by a. Okay, there it will be the pi by a, which is our lattice constant of the unit cell. So the Brillouin zone, I guess it will be discussed more in the next lecture, but if you remember that if you have a 1D lattice which has lattice constant of let's say a, then your first Brillouin zone will be between from minus pi by a to pi by a. Okay, this you can derive by basically making the reciprocal vectors of your 1D case, and then just finding the unit cell within your reciprocal lattice vector, and that unit cell will be your first Brillouin zone. Alright, so I guess it will be discussed more in the next week, but this was mentioned in the lecture as well, that the first Brillouin zone comes for a 1D case between k equals to minus pi by a to pi by a. Alright, so the maximum value of k is pi by a basically. Basically, alright, and so what we have to find? We have to basically find the number of possible k values in any energy band is in the first Brillouin zone. Okay, so basically within the first Brillouin zone we will have the energy bands. So this thing, okay, so this thing will be discussed more, I guess, in the next lecture. But this you might already know from a little bit of basic quantum mechanics, or if you have done a little bit solid state physics. Okay, but basically just consider that you need to find the number of possible k values, alright, within your first Brillouin zone, and your first Brillouin zone is from minus pi by a to pi by a, alright, and each of your k, uh, because of your periodicity of your lattice, that will be given by 2 and pi by l, alright. So thus the total number of around k values in the first Brillouin zone is given by, so that thing will be given by basically whatever the length of your Brillouin zone is, the length of the Brillouin zone divided by the length of each around k state. Alright, so here your length of your Brillouin zone is going to be from minus pi by 2 pi by a, so it will be 2 pi by a, alright, from minus pi by 2 to pi by length, and length of each around k value, so your k values are 2 and pi by l, so each k it occupies the length of 2 pi by l, alright, so that will be 2 pi by l. Okay, so you can say length of length occupied by length of, no, instead of length occupied by each. Okay, so total, so if you have to find the total number of k points within your around k points within your first Brillouin zone, in this case, so that will be equals to whatever the length of your Brillouin zone is, which is 2 pi by a, divided by the length occupied by each around k state, which is 2 pi by l. Alright, so using this, so that will be equal, that will give you l by a. That's your answers. Okay, so if your lattice is of length l and you have a lattice constant of a, the number of around k values in your first Brillouin zone, that will be given by this fraction l by a. Okay, any doubt in this problem? Okay, I guess Brillouin zone will be discussed in week 4 more properly, but this was, I guess, discussed like the Brillouin zone is for 1D is given by minus pi by 2 pi by where a is your lattice constant. Alright, so let's just do next problem, which is problem number 6. So in problem number 6, what we have is there is a 3% decrease in the Fermi level EF of sodium as the temperature is raised from 0 degree centigrade to 300 degree centigrade. Determine the volume coefficient beta, which is 1 by v del v by del t constant pressure P. Alright, so basically we so what we have here, so not we have, okay, we know, okay, I should write we know, okay, we know that our, so this is a 3D case. For the 3D case, we know that our Fermi energy, okay, so the Fermi energy will that will depend on, and it will depend on, it is given by h square kf square by 2m, and kf will be directly proportional to n to the power 1 by 3. So EF will be directly proportional to n to the power 2 by 3, where n is basically number of particles per number of this electrons per unit volume. Okay, so our EF will be, so basically our EF is directly proportional to n by v to the power 2 by 3. Alright, so this is we know. So let's say I write this, so that's a times n by v to the power 2 by 3, where a I am taking some constant, right? It will be some 2 pi or something, 2 pi to the power something. Now from here I have my EF, so I can write dEF by dV. Okay, so because basically we have to find this beta, and for beta we have to find it is given some del V by del T something. So there is some change in volume, we have to check, we have to find that volume coefficient. So and what is given to us that there is a decrease in the Fermi level, change in the Fermi level with respect to temperature T, when our temperature T has changed by some delta. So what we will do, we will do dF by dV here, and that will give us a times n to the power 2 by 3. I will just take like this, and what we'll have is minus 2 by 3 times 1 upon v to the power 2 by 3 times 1 by v. Alright, and here basically if I take this minus 2 by 3v, it is dEf by dv, and what I will have is this constant a n by v to the power 2 by 3. Now this is just my EF value, right? This is just our EF. So I will have dEf by dv is equals to minus 2 EF by 3v, right? I will have this thing. So from here, what I can write is I can write dEf by EF is equals to minus 2 by 3 of dV by dV. Okay, so this is like change whatever the like say infinite is small increase in increase or decrease, whatever the small change in EF divided by the value of EF. Okay, that will be equals to minus 2 by 3 times whatever the change is dV change in the volume divided by V. Okay, so this is the relation that we have derived. Alright, and then we have to find beta here. Now beta is given as to us as 1 by V del V by del T at constant pressure P. Now instead of del T we can take, okay, we are given a big delta here, so I can say that dV by V, whatever the change in V with respect to that volume V, if there is a change in delta T temperature, that would be given by this, right? So I can write dV by dV as beta times delta T. Alright, then using this, what I will have is dEf by EF is basically equals to minus 2 by 3 beta times delta T. Okay, so I can write my beta is equals to minus 2 by 3 delta T times dEf by EF. Alright, okay, now here it is given that, okay, here what is given to us is our Fermi energy EF has decreased by 3%. So there is a decrease of 3%. What does it mean? It means dEf by EF is basically equals to minus 0.03. Okay, so what I said that the Fermi energy has decreased by 3%. So it means dEf by EF, whatever change with respect to EF, that is divided by EF, that is minus 0.03. And also delta T, if I change this temperature into Kelvin, okay, we change always into Kelvin as well. Those 273 constant will cancel out. So basically delta T we have is 300. Okay, let's say Kelvin. Okay, because in Kelvin also the delta T will be 300. So from here we have now we have dE by EF minus 0.03 and delta T is 300 Kelvin. So our beta will be equals to minus 2 by 3 times 1 by 300 times this is equals to minus 0.03. So beta from here will come as 1.5 into 10 to the power, I have written 10 to the power minus you can write it as not 1.5, 15 into 10 to the minus 5 Kelvin inverse. So unit will be Kelvin inverse here, because dEf by EF is unitless and delta T we take temperature in Kelvin scale. So it will be 15 in 10 to the power minus 5 Kelvin inverse. Alright, so this is our answer. Okay, so this was our problem number 6. Okay, so let's go to problem number 7. Now what we have in problem number 7 is consider a solid of mass 26.98 gram per mole which forms a crystal with a BCC unit cell and the lattice constant A is equals to 331 picometer. So what is the density of the crystal? Okay, that has been asked to us. So find the density. First we know that volume of the unit cell in this case. So we have cubic. BCC is basically body centered cubic. If you don't know, BCC is body centered cubic. So let me just show you in case if you don't remember, if you have not seen. Let me draw a BCC unit cell for you. Body centered cubic. Okay, so this is a body centered cubic unit cell, and this is the conventional form of this BCC. Conventional because if you have a primitive unit cell, you just have one atom, you can say one atom or one lattice point per unit cell, but in this case we have two atoms. So this is our BCC. You will have each atom on the corners of a cube, and then you will have one at the center. Alright, one will be at the center. Okay, and this is your unit cell length A, that is given to us. Alright, that is constant A is given to us. Now from here we can find volume of the unit cell. That will be equals to A cube. That will be equals to 3.31. Now it is given in picometer, so it is 331 into 10 to the power minus 12 meter. Let me start from there. 331 into 10 to the power minus 12 meter whole cube. Now since everything is given in gram, we will find our it is asked that okay, the density is asked in gram per centimeter cube, so we will just convert it into centimeter. So it will be 3.31 into 10 to the power minus 8. Okay, 1 meter is equals to 100 centimeter. Okay, so we will multiply it by 10 to the power 4. 1 meter equals to 10 to the power 2. We will multiply it by 10 to the power 2, and then we will take this 10 to the power minus 2 here as well. So we will have 3.31 10 to the power minus 8 centimeter whole cube. Alright, and that will give you 3.63 into 10 to the power minus 23. Okay, centimeter cube. Okay, so this is the volume of our unit cell. Then mass of the solid. So basically we want to find the density. So what we are finding, we are taking our unit cell constant is given. So basically we are finding the volume of our unit cell. Then we will find whatever the mass is there per unit cell. So just divide that mass by volume, we will get our density. So mass of the solid in the unit cell, that will be equals to what we are given is that we have a solid which has 26.98 gram per mole is there. Okay, so we have the solid that we have, it is given that the mass of the solid is 26.98 gram per mole. So it will be 98 gram per mole divided by okay, and 6.023 into 10 to the power 23, which is the Avogadro number atom per mole. Okay, so per mole we have this many atoms, and the mass of solid is given in per mole, like per mole of atoms mass is this. So from here, so we will just divide it by Avogadro number, and we will get 4.48 into 10 to the power minus 23 grams per atom. Okay, so per atom mass, the mass of the solid per atom of the solid mass is given by this, and since there are okay, and we will multiply it by 2. Okay, this mass of the solid per atom. Okay, it is not in the unit cell, it is per atom. Okay, so this is the mass of the solid per atom, and since there are two atoms, in a BCC unit cell, so here you can see for a BCC unit cell, so we will have one atom in the center, okay, and each of these corner atoms, so a solid is made by this periodicity, so there will be other unit cell as well, in all the three direction, and each of these corner atom is going to be shared by the other unit cell as well. So each of these atoms at the corner, they will be shared by 8 unit cell. So basically number of atoms in BCC will be equals to 8 times of this 1 by 8. So these are the corner atoms plus 1. These are the corner atoms. Okay, plus, because each of this corner atom will be shared by 8 unit cell plus 1 which is at the center. So this will be equals to 2. So there will be 2 atoms in a BCC unit cell. Alright. So since there are 2 atoms in a BCC unit cell, okay, so we have mass of the solid. Now this will be the mass of the solid in the unit cell. In the unit cell, that will be equal to just 2 times of this. So that will be 8.96 into 10 to the power minus 23 gram. Okay, so now we have the mass of solid in the unit cell, and we also have the volume of the unit cell as well. Therefore, our density of the solid, so the density will be just equals to whatever the mass is, which is 8.96 into 10 to the power minus 23 gram, and the volume of the unit cell, which is 3.63 into 10 to the power minus 23 centimeter cube. So this will give you 2.47 gram per centimeter cube. Right. So this will be your answer, 2.47 gram per centimeter cube. So this will be the density of our solid. Alright. So let's go to our next problem, problem number 8. Alright, so in problem number 8, what we have to do is show that the reciprocal lattice vectors can be calculated by using the below formula. So these are the formulas. Okay, so these are important formulas, so you can use in your problem as well. So if you remember this formula, so like one of the problem that we solved, okay, we solved one of the problem where we find this reciprocal lattice vector. So there I didn't use these formulas, I just used the relation that ai vector dot bj vector is equals to 2 pi times del of ij. So this is the relation that we used, but instead of that we can also use this formula as well, these formulas as well, to find the reciprocal lattice vector. Alright, and here we have to prove that this formula works. So what we will do is we will just check that this formula satisfies this thing. Okay, so we have to make sure that if we write b1, let's say b1 vector in this form, then b1 vector is going to satisfy these conditions, and similarly then you can check it for b2 vector and b3 vector as well. Okay, so now we know that this, again I will just write what we know. A vector dot bj vector is equals to this 2 pi times del of ij, which means it is equals to 0 for I not equals to j, and it is equals to 2 pi for I equals to j. Alright, and here we have b1 vector. Okay, it is given by 2 pi times a2 vector cross a3 vector divided by a1 vector dot a2 vector cross a3 vector. Alright, this is what we have. Okay, and so we just have to check that okay, so we need to check that the definition of b1 vector satisfies condition 1. Okay, let's say this is our condition 1, satisfies 1. Okay, so they just so it just have to satisfy 1. So this we have to check. So first we will check b1 vector dot a1 vector dot a1 vector. What we will get? So we will get 2 pi times a1 vector dot a2 vector cross a3 vector divided by a1 vector dot a2 vector cross a3 vector. So that is equals to both of them will be same, so it will be, they will cancel out and we will get 2 pi. So here we are getting b1 vector dot a1 vector is equals to 2 pi. Similarly, we can check b1 vector dot e2 vector, that will be 2 pi. I will take out here e2 vector dot e2 vector cross e3 vector divided by e1 vector dot e2 vector cross e3 vector, and here e2 vector cross e3 vector is going to be perpendicular to both e2 and e3, so that will be 0. So we will have b1 vector dot e2 vector is equals to 0, and then we can check for b1 vector dot e3 vector as well. It's the same, e3 vector dot e2 vector cross e3 vector divided by e1 vector dot e2 vector cross e3 vector. Again, e3 vector is going to be perpendicular to e2 vector cross e3 vector, so it will be 0. So we have b1 vector dot e3 vector is equals to 0. Alright, so basically this definition of b1 vector is that satisfies this relation. So this definition of b1 vector is correct. Alright, and similarly you can check for b2 vector and b3 vector as well. So basically the purpose of this question was just to introduce you or remind you of these formulas as well, like how you can calculate the reciprocal lattice vector from the primitive lattice vectors. And mainly, even if you don't remember the formula, as you have seen in today's problem, if you just remember this relation, then also you can solve your problem. Okay, so this you can try on your own. Okay, you can just use these two definitions and check that these two definitions, they for b2 vector and b3 vector, they also satisfy this condition. Ai vector dot bj vector is 2 pi delta ij. Alright, let's go to problem number 9. So problem number 9 is we have to prove that the reciprocal lattice primitive vectors satisfy this relation. Okay, we have to satisfy this relation that b1 vector dot b2 vector plus b3 vector is equals to this 2 pi whole cube b1 vector dot e2 vector plus e3 vector. Okay, so we know. So for now, so for this problem, what I am going to use is I am going to use those formula for the reciprocal lattice vector that we have seen here. So in the next two problems, I am going to use these formulas now. Okay, for the reciprocal lattice vector, because that makes it easier to derive prove these relations. So from we know that I can write b1 vector as 2 pi times e2 vector cross e3 vector divided by e1 vector dot e2 vector cross e3 vector. Alright, this we know. Or let me just write these things in blue color. Okay, so we know b1 vector is equals to e2 vector cross e3 vector divided by e1 vector dot e2 vector cross e3 vector. Alright, so we will use this thing, and also we will also use this, like bi vector dot aj vector, that is equals to 2 pi times del of ij, which is 0 for I not equals to j and 2 pi for I equals to j. Right, so now we will try to prove this relation. So I will start from left hand side. LHS, so our LHS is b1 vector dot b2 vector cross b3 vector, so that will be equals to now I will write my b1 vector in terms of e2 vector and e3 vector. Okay, there is one 2 pi as well, sorry about that. This 2 pi times, right. So I will write 2 pi times e2 vector cross e3 vector, okay, e2 vector cross e3 vector dot b2 vector cross b3 vector, and I will have divided by e1 vector dot e2 vector cross e3 vector. Alright, and to solve this, we will use a vector property. Okay, a property of vector cross product. cross dot product. So this is the that A vector cross B vector dot C vector cross D vector. Okay, we have a similar kind of relation. We can see what we need to solve between A and B. So this is given by A vector dot C vector times A vector dot C vector times B vector dot D vector minus A vector dot D vector times B vector dot C vector, right? So continuing with our LHS, now using this relation I can write this 2 pi times, okay, A2 vector, okay, you can see here, okay, this will be E2 vector dot B2 vector times E3 vector dot B3 vector minus E2 vector dot B3 vector and E3 vector dot B2 vector, right? This whole divided by E1 vector dot E2 vector cross E3 vector, right? So from here, okay, now what we have is, okay, now we know that this thing, okay, this E2 vector dot B3 vector, that is going to be 0, and this E3 vector dot, okay, let me just use another color, say green. So this will be 0, and E3 vector dot B2 vector, that is also going to be 0, and these things, this, let me just, here, E2 vector dot B2 vector, that will be 2 pi, and A3 vector dot B3 vector, that will be 2 pi. So what we will get? We will get 2 pi whole cube divided by E1 vector dot E2 vector cross E3 vector, and that is our RHS in this what we have to prove. Okay, so that is equals to our RHS, and hence put, right? And there is a I guess there's a problem in your assignment as well this week. So just a hint for that, that you can take a hint to solve that problem. That this modulus of E2, this thing, modulus of E1 vector dot E2 vector cross E3 vector, this is basically the volume of your primitive unit cell. Okay. So E1 vector dot E2 vector cross E3 vector that we have here in this relation, that is actually the volume of your primitive unit cell. So this will help you to find out the relation between the volume of your primitive unit cell and the volume of your reciprocal unit cell, right? So hopefully, like you will be able to solve that this week's problem now. Alright, so let's go to problem number 10 now. Okay, so in problem number 10 what we have, suppose primitive vectors are constructed from the BI in the same manner as the BI are constructed from the AI. Prove that these vectors are just the AI themselves, that is show that this relation. So basically what it is saying is that this problem, let's say the reciprocal lattice vector that we have found, they are now the roles are changed. Basically your BIs are now your AIs. Okay, so you using whatever the reciprocal vectors that we had, that we have seen, like our BI vectors. If we consider our BI vectors as our primitive vectors in the real space, then we have to show that if we form the reciprocal lattice vector. So basically if you form a reciprocal lattice vector from your reciprocal lattice vector, then that is going to be your primitive vectors itself. So if you form, okay, so that is what it is saying. So BIs are our reciprocal lattice vector, and if we form reciprocal lattice vector from this reciprocal lattice vector, considering this bi's as our primitive vectors, then our then reciprocal of lattice vectors of these reciprocal lattice vectors are going to be your primitive vectors AIs that we started with. Okay, so that is what we have to prove. So basically there will be like so basically we have to prove this relation, like if we have this bi vectors, then if we find we know, like if we have the AIs as our primitive vectors, we found the reciprocal lattice vector using a similar formula, where instead of b's here we have b's, instead of b we had a's there, which is 2 pi times that b1 vector is equals to 2 pi times e2 vector cross ac vector divided by a1 vector dot e2 vector cross e3 vector. Now similarly we have to prove that if we are using this b vectors as our primitive vectors, then this formula will give you your initial primitive vector a1 vector, so the reciprocal vectors. So by that it means that the reciprocal lattice vector that will be formed from this reciprocal vectors will be our initial primitive vectors. So I will just prove this relation, and the rest of the relations that you can derive on your own. Okay, so rest of the relation will be like 2 pi times this b3 vector cross b2 vector, b3 vector cross b1 vector divided by b1 vector dot b3 vector b2 vector cross b3 vector, that will be equals to your e2 vector. And similarly you will have 2 pi times b1 vector cross b2 vector divided by b1 vector dot b2 vector cross b3 vector, that will be equals to your e3 vector. Okay, so this two you can try on your own. Alright, so this is the extra part, and right now yeah we'll just prove this one. Okay, because and the solution will be similar, so that will prove that if we form the reciprocal lattice from the reciprocal lattice vectors, then the lattice vector for that lattice will be the same as our primitive vectors. Alright, so to prove this, again we will need these things. So again we know that this stuff we know. So I will use b3 vector, definition of b3 vector, which is 2 pi times e1 vector cross e2 vector divided by e1 vector dot e2 vector cross e3 vector. Right, and also we know that ei vector dot bj vector is equals to 2 pi times del of ij is equals to 0 for I not equals to j, and 2 pi for I equals to j. Alright, so here basically we have to prove this. So I will start from again LHS. So now LHS is given as 2 pi times b2 vector cross b3 vector divided by b1 vector dot b2 vector cross b3 vector. Okay, so now I will write b3 basically in terms of these AIs. So I will have 2 pi times b2 vector cross, now instead of b2 vector I will write 2 pi times e1 vector cross e2 vector. Okay, divided by e1 vector dot e2 vector cross e3 vector, this divided by b1 vector dot b2 vector cross b3 vector. So we will have 4 pi square, I will have b2 vector cross e1 vector cross e2 vector divided by b1 vector dot b2 vector cross b3 vector and e1 vector dot e2 vector cross e3 vector. Right, now to solve this here we will again need relation from vector products, which is like E vector cross B vector cross C vector, that is equals to b vector times a vector dot c vector minus c vector times a vector dot b vector. Alright, so using this relation, what we will have, let me just write it as 2 pi square now, 4 pi square. What I will have is a1 vector times b2 vector dot a2 vector and minus e2 vector b2 vector dot a1 vector. Alright, now here again this b2 vector dot a1 vector, that will be this is b2 vector. Okay. Now again this will be equals to 0. Okay, b2 vector dot a1 vector will be 0, and this one b2 vector dot e2 vector, this will be 2 pi. So and also we have in the denominator we have b1 vector dot b2 vector cross b3 vector, and I have e1 vector dot e2 vector cross e3 vector. So from here what we have basically 2 pi whole square, whole cube now. Okay, we have 2 pi here as well, times e1 vector divided by b1 vector dot b2 vector cross b3 vector. Okay, here you must have seen that. Okay, I use b3 in terms of a1 a2 only in the numerator. I am keeping the denominator as fixed for now, and you will see why. Okay, we do not need to write b3 as in terms of a in the denominator. Okay, okay, so we have this relation, and now we need to find its denominator. So so we just proved one relation in the previous problem, that okay, so we proved this relation just now, that b1 vector dot b2 vector cross b3 vector, that is basically 2 pi whole cube e1 vector dot e2 vector cross e3 vector. That's why I can write this e1 vector dot b2 vector cross b3 vector times e1 vector dot e2 vector cross e3 vector, that will be basically equals to 2 pi whole cube. Alright, so that was the reason why I didn't put the definition of b3 in terms of ai's in the denominator, because denominator is basically just going to be 2 pi cube. So that's why this will become 2 pi whole cube, numerator was 2 pi whole cube e1 vector. Alright, and now the denominator will be also be 2 pi whole cube. So we get e1 vector, and this is our RHS. So this is our hence proved. Alright, so okay, so and similarly you can prove this extra part, this acceleration as well. For that we can make, this is how we can make a2 and a3 from this b1 b2 b3. Alright, okay, so let's go to problem number 11. Okay, let's just solve this problem number 11 and 12, and then we will try to discuss a little bit about net assignment as well. Okay. So let's just solve this problem number 11 and 12. Okay, so in problem number 11, so this is this problem is for this. Okay, so if you have any doubts in quantum mechanics, if you just want to, like, if you don't remember something, you want to brush up your concept on quantum mechanics, so this is the book that I earlier mentioned as well, Introduction to Quantum Mechanics by David J. Griffiths. So these two problems, they are from that book only, and these problems are on bracket notation. So hopefully you will get a little bit practice from this problem, but it's better to and if you want to learn about that or brush up about on these topics, then you can go to this reference book. Alright, so basically in this problem, which is from this book, what we have is consider a three-dimensional vector space spanned by an orthonormal basis 1, 2, 3, where we have gets alpha and beta are given. Okay, so we have a three-dimensional vector space which is spanned by orthonormal basis 1, 2, 3. What does it mean is that if we have any wave function, okay, basically in Dirac notation we define wave function in form of this gets, okay, this get notations, and there is also this bra notation, which is basically the you can say complex conjugate kind of stuff for these vectors. And generally when you take this basically each of these cat we represent as these column vectors, let's say some psi 1, psi 2, psi 3, alright, and then the bra of this will be represented as a row vector and also with a complex conjugate psi 1 star, psi 2 star, psi 3 star. Alright, so this is some this thing we don't need for this problem, but I guess there is a problem on matrix multiplication in the assignment, so just a reminder for that. Okay, so you can write these things like this. Okay, so okay, so what is given to us? We have an alpha and beta wave functions are given like this. So first problem is we need to find this bra of alpha and bra of beta in terms of this bra 1, bra 2, bra 3, which will be in the dual basis. Okay, because 1, 2, 3 are forming your real basis, then this bra 1, bra 2, bra 3 will form your dual basis. Okay, so for this if I have to form bra of alpha, so basically that will be equals to, okay, so that will be equals to you just have to take whatever this is, so this cat will become your bra of 1, and you have to take the complex conjugate. So basically this, so basically bra of alpha will basically you have to take each of them, you have to take, basically you can say this is a complex conjugate of this. So basically you can say that we write it like this: minus 2 times of 2 minus iota of 3 cat times, you can take the complex conjugate. Now complex conjugate of iota will be minus iota, and cat of I will be bra of cat of 1 will be bra of 1. For 2 it will be 2 bra of 2. For iota it will be minus iota, it will be plus iota bra of 3. Okay, so this is how your bra of alpha will be given by this. Okay, so so this is how you solve it. And for bra of beta will be again just take the complex conjugate of your cat of beta, and cat of beta is given to you as iota times cat of 1 plus 2 times cat of 3. Take the complex conjugate, so that will be minus iota times bra of 1 plus complex conjugate of 2 is just 2 times bra of 3, right? And then let's go to part B. So then we have to find this notation, this bra alpha cat beta, which is just a dot product between alpha and beta, and bra beta cat alpha, and confirm that this bra beta cat alpha is equals to alpha beta, this complex conjugate. Alright, so if you find this, okay, so we have the definition of bra of alpha. So bra of alpha is equals to minus iota times cat of 1 minus 2 times cat of 2, or let me just write this, the bra of beta is equals to this. Right. Okay, so bra of alpha is minus iota bra of 1 minus 2 times bra of 2 plus iota bra of 3, and also these are orthonormal bases. Okay, it is given that these are orthonormal bases, so remember that this ij is equals to del of ij. Okay, it means these are 0 for I not equals to j and 1 for I equals to j for this cat 1, 2, 3, the orthonormal basis. So this will be, and the cat of beta is given here, it is iota times 1 cat of 1 plus 2 times cat of 3, right? So this will be equals to so I will take first this and this, so this will be equals to minus iota square, I write like this, 1 1, this will be minus 2 iota 1 3, then we have minus 2 iota 2 1, and minus 4 2 3. Alright, okay, and then we have plus iota square 3 1 and plus 2 iota 3 3. Right, and here what you will have, this will be equals to 1, this will be equals to 0, this will be 0, this will be 0, this will be 0, and this will be 1. So what we will have, okay, because of this relation, okay, ij bra I cat j will be equals to L of ij, because these are orthonormal bases. So what we will have, iota square will be minus 1, so I will have a plus 1, and here I will have 2 iota, right, yeah, so it will be plus 2 iota, so I will have 1 plus 2 iota, so this will be my alpha beta, bra alpha cat beta. Okay, now we have to find bra beta cat alpha. Now bra beta we have found as minus iota bra of 1 plus 2 times bra of 3, and cat of alpha is given to us iota times cat of 1, and minus 2 times cat of 2 times cat of 2, and we have minus iota times cat of 3. Right, so here we will have minus iota square cat of 1 bra of 1 cat of 1, then we will have plus 2 iota bra of 1 cat of 2, then okay, sorry, let me just make this again, minus iota square bra of 1 cat of 1, then minus 1 plus 2 iota bra of 1 cat 2, then we will have minus 1 plus iota square bra of 1 cat 3, then plus 2 iota bra 3 cat 1, then minus 4 bra 3 cat 2, and minus 2 iota bra 3 cat 3. Alright, and here again what we will have, this will be 1, this will be 0, this will be 0, this will be 0, this will be 0, and this will be 1, and iota square will be minus 1, so we will have 1, we will have 1 minus 2 iota. Okay, so 1 minus, so this will be our beta alpha, and here we can check that this is basically, this 1 minus 2 iota is basically complex conjugate of 1 plus 2 iota, which is our alpha beta complex conjugate. Right, so this we have to prove. Okay, this we have to prove that bra alpha it will be equals to complex conjugate of this. Okay, so this was our part B, and part C is find all 9 matrix elements of the operator E. Find all the 9 matrix elements of the operator E cap alpha beta, alpha cat and beta bra beta, cat alpha bra beta in this basis. Okay, in the basis which is basis 1 2 3. Right, this we have to find, and then we have to construct the matrix, and then we have to check that if that matrix is Hermitian or not. So for that basically for each of this matrix element, let's say A11, that will be this bra of 1 E cap cat of 1, and here we have E cap is basically our where E cap, sorry, so basically let me just first write E cap. So E cap is equals to cat alpha bra beta. Okay, we have this cat alpha bra beta, and we have to find this in the matrix form of this operator in the orthonormal basis. So for that I will find all the matrix elements. So that will be 1 E cap 1, there will be 1 alpha beta 1. Okay, and alpha beta we have found. Okay, what are our ket of alpha, ket of beta? So let me just write them. Okay, let me just write them here as well. So ket of alpha is iota ket of 1. Okay, let me just write the definition as well so I can write this relation properly. So we have to use these relations. We have ket of alpha is equals to iota times ket of 1 minus 2 times ket of 2 and minus iota times ket of 3. And similarly we have draw of alpha is basically minus iota times draw of 1 minus 2 times draw of 2 plus iota times draw of 3, and ket of beta is equals to iota times ket of 1 and plus 2 times ket of 3. And similarly we have draw of beta is equals to minus iota draw of 1 plus 2 times draw of 3. Alright, so using this definition of alpha beta, we can find the matrix elements. Let's say we need to find A11, so that will be 1 A cap 1, and A cap is basically your this is alpha beta, right? Ket of 1, so you will have 1 alpha and beta 1. And if you do that, so if you take this bra of 1 on this alpha, and remember that is 1, 2, 3 are orthonormal bases, so you will get only the component from, let's say, from 1 only. So you will get an iota from here times bra of beta. Here is our bra of beta, and I will put a ket of 1 with it, so that will be minus iota. So we will get a 1 from here. At a square with minus 1, we get 1 here. Okay. Similarly, you have to find all the 9 elements. So what is the time? Okay, it's already 7:52. So let me just find one more element. Okay, let's say like A12 you have to find. So that will be 1 A cap 2. Okay, so that will be 1. Again you have alpha, you have beta, you have ket of 2, 1 alpha beta 2. So let me just write it. Okay, and alpha basically you can write alpha. Okay, let me just write just this one in a proper way so that you understand what we are doing. So we have, okay, we have ket of alpha here. So ket of alpha is written as iota times ket of 1 minus 2 times ket of 2 minus iota times ket of 3. Alright, so this is one thing that we have, and the other thing we have is bra of beta, and bra of beta is equals to minus iota times bra of 1 and plus 2 times bra of 3, and we have ket of 2 here, right? Okay, so from here what we get, you get iota times 1 1 minus 2 times 1 2 minus iota 1 3, and from this one, the other one, you will get minus iota times 1 2 plus 2 times 3 2. Okay, and here we can see that what we will have here is this will give you 1, this will give you 0, this will give you 0, and 1 2 and 3 2 will give you 0. And since this is in multiplication, so if this is 0, so overall this thing is 0. So matrix element A12 is going to be 0, and A11 we found that A11 was 1. Okay, so similarly in this fashion, basically to find this matrix element A, you have to find all these matrix elements. To find this matrix A, you have to find this A11, A12. Similarly, you have to find A13. Then you will have to find A21, A22, A23, A31, A32, A33. Alright. So you will have to find all these 9 elements. So you can try this on your own. Okay. the thing will be same, like A11 is defined as 1 A bra of 1 A cap cat of 1, and A12 is defined as bra of 1 A cap cat of 2. Similarly, you can say that, for example, A23 will be basically bra 2 A cap cat 3 will be 2 alpha beta 3. Alright, and then you have to just solve in the similar fashion as we have solved for other elements. Alright, and if you solve it, so I will just give you the answer, and you can try this on your own. The matrix that you will get is, we already find this two matrix element 1 0, and if you find the rest of one, it will be 2 iota 0 minus 4 minus 1 0 and minus 2 iota. Alright, so this will be your matrix A. Okay, you can do it on you can do for the rest of the matrix elements. Try to do this on your own. Okay, the method will be the same. Alright, so this is our matrix. Now other thing that is asked in the question is that we have to check whether this is a Hermitian or not. Okay, so if you remember, the matrix is Hermitian if is A adjoint, basically the complex, you take the transpose of the matrix and you take the complex conjugate, that should be equals to this. If this is happening, then it is Hermitian. Okay, so to be a Hermitian, A adjoint should be okay, A adjoint should be equals to A. So basically you have to take the transpose of this matrix. Okay, so this will be basically take the transpose of this matrix and then the complex conjugate. So first I will take the transpose of this. Let me just write it like this. So it is A transpose, and you take the complex conjugate of that. So now A transpose is basically, if you take the transpose, it will be 1 0 2 iota 2 iota 0 minus 4 and minus 1 0 minus 2 iota. Alright, then you take the complex conjugate of this, it will be 1 minus 2 iota minus 1 0 0 1 minute, yeah, this will be 0 0 0 now, and this will be minus 2 iota minus 4 and 2 iota, and this we can see that it is not equals to A. Okay, this is not equals to our A matrix. Okay, here you can see that whatever our A adjoint is, that is not equals to A, so A is not Hermitian. So we can see that here A, this adjoint is not equals to A. Therefore A is not Hermitian. Alright, so to prove Hermitian, you have to take this here, take the transpose of the matrix and you take the complex conjugate. Alright, so this was our problem number 11. Okay, let's go to problem number 12. So in problem number 12, okay, again this problem, and this is also taken from David J. Griffith's Introduction to Quantum Mechanics. And what we have here is the Hamiltonian for a certain two-level system. It is given as Hamiltonian is given as some epsilon times bra 1 ket 1 minus this form, where again 1 and 2 are the orthonormal bases. Okay, so they are orthonormal to each other. So that's why 1 1 will be equals to 1 1 2 2. This 2 2 will be equals to 1. And this 1 2 equals to 2 1 will be equals to 0. Alright, and this epsilon is a number with the dimensions of energy. Okay, this is just a number with the dimension of energy. We have to find its eigenvalues and eigenvectors. Okay, as a linear combination of 1 2, and what is the matrix H representing H cap with respect to this basis. Okay, with respect to this basis psi. Alright, so for this what we can do is we can write. So basically we have to write the eigenvalues and eigenvectors, and they will be in this form of this orthonormal basis. So we can write the eigenvector as ket of psi is equals to C1 times cat of 1, some constant C1 times cat of 2, and some constant C2 times cat of 2, and call the this is epsilon there, and call the eigenvalue as E, alright, as capital E. Then the eigenvalue equation is we have h cap of psi, okay, and that will be equals to basically we know h cap of psi will be equals to E psi, okay, and our psi is basically equals to so h cap of psi, now h cap of psi is given as this epsilon times the energy eigenvalue and this energy eigengets, and h cap psi, so that will, so h cap is given to us, so h cap I will write it as this whatever epsilon is times cat 1 bra 1 minus this it is I have written it like this, not 2 plus cat 1 bra 2, and we have cat 2 bra 1, alright. This is our h cap that is given to us times our psi, and psi we are getting as C1 times cat 1 plus C2 times cat 2, alright. So from here if you write h cap psi, now basically the eigenvalue equation, so eigenvalue equation that we have is h cap psi will be equals to, if our energy eigenvalue is E, then this is the eigenvalue equation, okay. So I am writing right now the left hand side, which I can write like this, and from here what we can see is that if you again, okay, so like we have done in the previous one, so basically you will have a bra 1 and this bra 1 and cat 1, this will give you 1, while if you take this dot product, this products bra 2 and cat 1, or here also bra 2 or cat 1, they will give you 0. Only these bra 1 and cat 1, bra 1 and cat 1, those products are going to give you a 1, alright. And remember that in quantum mechanics the order is important, so you just can't switch this 1 to and 2 1, so they will remain in this form only, okay. So from using this and this we will get C1 times this 1, because this bra 1 and cat 1 will give you a 1, alright. And if you use this bra 2 and cat 1 will give you 0, so this will not give you anything. This bra 2 and cat 1 will give you 0 again, and this bra 1 and this bra 1 and this cat 1, this will give you again 1. So from there we get plus C1 times cat of 2, right. Similarly if you do for this bra 1 and cat 2 will give you 0, okay. Same thing, this bra 2 and cat 2 will give you 1, so you will get plus C, actually no, minus, here there is a minus sign, minus C2 times cat of 2, and then this bra 2 and cat 2 will give you 1, so you have plus C2 times plus C2 times cat 1, yes, cat 1 here, okay, this times cat 1, and this bra 1 and cat 2 will give you a 0. So you will have this thing. So here we can basically we can write now as epsilon times, taking C1 as common, so you can take this as C1 times cat 1, taking cat 2 common, okay. So I can write it as C1 plus C2 times cat of 1 plus C1 minus C2 times cat of 2, alright. this by your eigenvalue equation. It will be given by E times ket of psi, alright, and your ket of psi is basically C1 times 1 plus C2 times 2. This is how we have to find our ket of psi, alright. So from here, okay, so let me just write it like this. Okay, so this is basically our LHS. This is your LHS, alright, and your LHS is this, and this is your RHS. Now do LHS equals to RHS. Okay, and if we do LHS equals to RHS, what we get is we get epsilon times C1 plus C2 times ket of 1 plus epsilon times C1 minus C2 times ket of 2. This is equals to E times C1 times ket of 1 plus E times C2 ket of 2. Alright, so just match the coefficients of ket of 1 and ket of 2 here. We get epsilon times C1 plus C2 is equals to E times C1. Okay, E times C1. So from there you can get C2 equals to E by epsilon minus 1 times C1. Right? So C2 we can get in terms of C1, and similarly if we take the coefficients of this ket of 2, we have epsilon C1 minus C2. Okay, already we get epsilon C1 minus C2 equals to E times C2. So from here we can get C1 is equals to E by epsilon plus 1 times C2. Okay, and we already have found what C2 is in terms of, we have found so we will use this C1 value in this definition of C2. So I will use this in there. So from here we have C2 is equals to E by epsilon minus 1 times E by epsilon plus 1 times C2. Okay, so C2 will cancel out on both sides. So you will have basically E by epsilon minus 1. So basically, sorry, this will be, so just multiply this, it will be E by epsilon whole square minus 1, which is equals to 1. Okay, A plus B times A minus B, A square minus B square. Okay, just now 1 minute. Okay, so from here we get our energy eigenvalue will be equals to 1. Sorry, it will be equals to epsilon plus minus it will be root 2. Okay, plus minus root 2. It will be plus minus root 2 times epsilon. So this will be epsilon is that was just some number here in it is our Hamiltonian, and our energy eigenvalue will be equals to plus minus root 2 times of this epsilon. And then the eigenvectors we have to find. The eigenvectors are so here we have C2. So we have the relation C2 is equals to E by epsilon minus 1 times C1, and E we have found plus minus root 2 times epsilon. So from there we get C2 is equals to plus minus root 2 minus 1 times C1. Okay, so you can write this psi plus minus wave function will be given by C1 times ket of 1, and instead of C2 I can write plus minus root 2 minus 1, and C1 I have taken common as ket of 2. Alright, and so basically this is okay. So this will be your eigenvectors. Okay, so these are going to be our eigenvectors. Okay, and you can find the C1 value by normalization. So since we are already out of time, I will not solve it complete here. But basically, if you want to find the matrix H, okay, the other that we have to do is, what is the matrix H representing H cap in the respective bases. So basically, the matrix H, as we have found earlier, will be equals to the given by H1 H, I will say plus plus, H plus minus, H minus plus, and H minus minus, where basically each of this matrix element is like H plus plus will be equals to psi plus H cap psi plus. Okay, so you have to do psi plus H cap psi plus. Similarly, your H plus minus will be equals to psi plus H cap psi minus. Right. So that is how you have to solve it. And since this will be eigenvector in this basis, okay, 1 minute. This is given that what is the matrix element H cap representing H cap with respect to this basis. Okay, sorry, we have to find it in this basis actually, not in the eigenvalues. Okay, so eigenvalues we already have. Sorry, my mistake. So we have to find this in this basis actually. Yeah, so you have to find this thing. Sorry about that. So in the problem, what has been asked is, okay, basically the H will be a diagonal. Okay, since okay, so that is also interesting. Okay, remember that this H will be just equals to this energy, which is to us plus minus root 2e. Let's say plus root 2 epsilon 0 0 minus root 2 epsilon. Okay, let me just write it down. Okay, so I made a mistake. So this is not asked in the question, but basically if we write our this Hamiltonian in the taking this eigenvectors of that Hamiltonian as our basis, basically if you find this thing, what I was saying, if you find this thing minus minus, where your H plus plus is basically your psi plus H cap psi plus. So since and like this H plus minus will be equals to H plus minus equals to psi plus H cap psi minus. So this matrix will be just equals to, let's say it will be equals to root 2 times epsilon 0 0 minus root 2 times. You don't need to solve it because this the matrix will be ortho. It will be this. It will be diagonalized. It will be diagonal. It will be diagonalized if you take your eigenvectors as your basis to find this matrix elements. Okay, if you take this eigenvectors to find this matrix elements of your Hamiltonian and of your operator of any operator, basically if you take the eigenvectors of that operator, then also it will be diagonal, and for the Hamiltonian also it will be diagonal. So in that case it will be just this. Okay, root 2 epsilon 1 0 0 minus 1. But what is asked is this. Okay, in the problem it is asked this. You have to find this one. Okay, you have to find this in this basis. Okay, you have this orthonormal basis of 1 and 2, and you have to find this within this basis actually of 1 and 2. So if you calculate it, so just try to calculate it, give it a shot, and I will solve it in the next class, because Hamiltonian is given to us and you have 1 and 2. Okay, you do know that they are orthonormal and all. So what you will get is E times what we have found. What you will find is it will be given by epsilon times 1 1 and 1 minus 1. So it will not be diagonalized in this basis, but it will be diagonalized in your if you write it in the basis of its eigenvectors. Right. So just try to solve it. Alright. So this was our last problem. Okay, we are already out of time. So let me just stop sharing this one on my tablet. Stop sharing. Okay. So we are already actually out of time. But what was the problem that you want to discuss? Okay, just let me just go here. Okay, yeah, you can see my screen, right? Okay, so this week assignment, right? So we can just quickly discuss. We are already out of time, but let us discuss quickly. 1 minute. Why this is not opening? Week 3 assignment. Alright, yeah. So question number, which question number? Question number 2. 2, 3 and 8. 8 one is this one. Okay, the translation operator Tx can also be defined in terms of the moment operator Pk, then which of the following is true. So this one actually, this question number 8, you have to try on your own actually, because I cannot give you the hint right now regarding this one. Okay, so if you have to, yeah, 2 and 3. Okay, for a second one, I can guess you can try out 3 on your own. There is no much you have to do. Okay, but for question number 2, basically, like it is a considered system. You are given this psi 0 is given in this as a row vector, as a vector. Okay, and your Hamiltonian matrix is given to you, given, and you have to find the total energy of the system at t equals to 0. So for this, so let me just stop sharing and give you. So for this, you just have to. So I can't give you the exact solution right now for this month. Okay, we can't discuss them, but let me just see. Okay, you can see my screen. I'm sharing right now, right? Okay, yeah. So let me just make a new page. Rough. Let's just call it rough something. So basically, you had to find this average energy, right? You have to find the total energy of the system at t equals to 0, and you have given a psi of psi at t equals to 0 is given. So here, this average energy is basically will be given by psi of 0 at t equals to 0. You have to find h cap psi of 0. All right, and psi of 0, it's given to you in some form of this column vector. Okay, this column vector, and your bra of psi of 0, as I just briefly discussed. So let's say there is some like a1, a2, a3 that is given to you. So your bra of psi 0 will be just a1 star, a2 star, and a3 star in your row vector. Alright, and let's say you have some h in some other basis, you have it in some matrix form. Alright, so basically this will be similar to your matrix multiplication. So what you have to do is you have to just take a matrix multiplication here, whatever your a1, a2, a3 is, and then whatever. So this will be your bra actually. Sorry. So bra of psi 0, you have to take a1 star, a2 star, a3 star. Okay, whatever you is. Then you matrix is given to you. Okay, so take your H matrix here. This is your H matrix, and this will be your this cat. Okay, a1, a2, and a3. All right. So to solve that problem, you have to basically do this kind of multiplication. Okay, you have to do this this row vector times this matrix times this. Okay, so this is your 1 cross 3, this will be your 3 cross 3, and this is your 3 cross 1. Okay, so from this you will get an average energy. Okay, you will get some constant value. Okay, you will get some average energy E, which will be 1 cross 1. Okay, you will get some average energy value basically. Alright, to solve this problem. So that is just by this definition. What is the average energy definition is, and how to write this. If you are given a cat is given like this, a column vector, and your bra will be given by this kind of row vector, that will be a1 star, a2 star, and a3 star, and your matrix is already given there. So if a matrix is given in some other basis as well, so you have to basically do this matrix multiplication, simple matrix multiplication, and then you can get your average energy. Alright, so hopefully you can solve that problem now. Okay. Yes. And 10. Just 1 minute. For a nearest neighbor tight binding model in 3 dimensions, the bandwidth is 6. We actually can't discuss these problems right now. So because we are already actually out of time as well, and these are like this week assignments, so we cannot discuss them right now. So just try to solve them. So I have given you a hint for this one, and for the rest other parts, I guess basically I hope you understand what is the meaning of bandwidth is just that as solved for the tight binding problem in graphene. if you remember, I saw in graphene you had some u of energy was given by minus 2t cos of theta. So your value was going from this something 2t to minus 2t to 2t. So that is your bandwidth. So you have to find this kind of bandwidth here. And it is just asking that if the same thing, so epsilon naught is 0 in this case. Okay, so for 2D case that has been solved. Okay, now you have to do the same thing in the in the 3 dimensions, right? So just try to find out this the same relation that you find in this case. So just in 3D, remember that, okay, basically, and you have to do the, when you will write this equation. So in 2D case, what this was in actually 1D case what you obtained. You have just t here and t here. Okay, so you have just two terms there. When you go to 2D, you will have this. You will have basically, you will have 4 nearest neighbors, while if you go to 3D, you are going to have now 6 nearest neighbors. Okay, so you will have 6 nearest neighbors. All right. So just remember this thing. Okay, so to solve this thing, basically you are going to have, when you were doing this thing in 1D, you were having only 2 nearest neighbors. If you go to 2D, you will have 4 nearest neighbors, and when you go to 3D, you will have 6 nearest neighbors. Then you have to write your matrix that you have written for the 1D case. You just have to write it in terms of considering that there are going to be 6 of them. There are going to be 6 nearest neighbors now. All right. So just try to do it. Okay. So this hint I can give, like, and the bandwidth will be just whatever the relation you will get. The bandwidth is just that difference one. Okay. And question. Consider a one-dimensional lattice with a weak periodic potential. The gap at the edge of the Bernoulli zone is okay. So basically, for the Bernoulli zone, yeah, I can just say that, okay, you know, this also I can't discuss right now, but maybe in the I have one question for the two-dimensional case as well, but we can discuss it. We will discuss that question in the next section, next session, when this assignment submission will be done. But basically, I can just, like, you have to take your edges of the Bernoulli zone is just minus pi by 2 pi by 8. So for this also, just try it out this time. I can't give you hint for this one. Just try it out, and in the next session, yeah, we'll try to solve if the submission date is afterwards, right? So if the submission, you can see this solution. Yeah. Next session date will be next Saturday only, so it will be after the submission of this week assignment. Okay, so I could not discuss this problem right now, but maybe in next time. Okay, and next time I will try to find, there was some problem in 2D, so in next session I will solve that 2D problem, so that will be that will give you much more clarity on that kind of problem. Okay. Question number. Just try it this time. We can't discuss, actually we can't discuss this week assignment in this week's session actually. So that's the that is like the guideline basically. I can't discuss those problems, but I was just giving you a little bit hint that I can give for those. But before submission, we can't discuss actually. That is, we can't do it. That is the guideline that is given to me. Just try it. That is this week assignment. Yeah, that is the thing. I can't discuss this week assignment right now. Okay. Okay then. No. Okay. Okay. Let's just end today's session, and just try your best on this week assignment. Okay. Okay. Yeah. So basically, if you go to so all this whatever I write, so you don't need to write the question and question I guess, because let me just stop sharing. So all these things. First of all the recordings, they are also being shared on the YouTube. I hope you can access them. And yeah. Okay, okay, okay. Yeah, but for sharing it, that's a problem. I don't know like how to share. I don't have the uh, access to the mailing list actually. I don't have that kind of access. No. I can't upload it. But after the sessions actually, just 1 minute. After the session, so whatever I write during the session. So let me just share it again. So whatever I write here, you can see my screen. Okay, so there is this section here. You can see problem solving session. So if you go to this problem solving session, so there is within this Excel sheet there are actually links to the YouTube links. If you go to this, let me just share this. Okay, so if you go to that link, so this Excel file will open. So in this Excel file, there are links to the YouTube recordings, okay, and then there is link for this Google Drive folder as well, okay. This is uploading actually. Okay, there's this link as well. So you can go to this link to the drive. Yeah. During starting, that I will try to do. But basically, after the session, you can find within this Google Drive. Uh, you can find the PDF for the session. Okay, this is not opening right now, but yeah. So okay, so there is this PDF file. So in this PDF file, like this is for the week 2 one, and then in this PDF file, whatever I have discussed during that week, that is there. It's not okay. That will be there. So yeah, you don't need to write the questions. Okay, the questions that you can find from this PDF as well. The problems and solution, and you will also have the recording, and yeah, I will try to upload one of these PDF without the solutions, basically just with the questions. Yeah, I will try to upload it on the Google Drive. Okay, correct. Yeah, okay. Yeah, yeah, I tried to do that. Yeah, I tried to do that, but I couldn't find this time problems related to them. But I will try to do that thing. Okay, what you have said. I try to do this, but I have to search for problems in the books and all. So I couldn't find it this time. But yeah, sure. Yeah, I will try to find problems which are similar. But sometimes actually like there are problems, but then you can basically if I solve like in the previous session as well, there was one problem which if you have seen that if I solve that problem, it was actually very similar to the that week assignment. So sometimes like if I solve that problem, those problems will directly give you the not only hints, like the problem that I found, like it not only gives you the hint, it actually basically solves the problem. You can just guess the answer from there. Uh, but but I will try to find some similar problems like that. It will not exactly solve the problem, but gives you just the hint of that week assignment. Yeah, we can try to do that. Okay. Okay then. Okay, let's and let us end today's session then. Okay, thank you.